So before we begin, let me fix a small mistake we had. When we spoke about very weakly dominated strategies, the reason I defined them, the main reason is that there was this proposition that iterative deletion of finitely many very weakly dominated strategies introduces no new mixed Nash equilibrium. The same actually as for just weakly dominated. And that's true, but it requires another condition that they're deleted one by one. Because you don't want to delete, let's say, two equal strategies such that each one of them very weakly dominates the other one, so they're both very weakly dominated. But then we delete both of them, and there is nothing left which dominates them. Maybe there is nothing left. That's the problem. Because remember how we argued why that introduces no new mixed Nash equilibrium. Because we added no new strategies. So the only way to introduce new mixed Nash equilibria would be to discredit previously possible deviations. So we may not delete anything without leaving something which is at least as good. That's what we use when we spoke about weak domination. But when we speak about very weak domination, that's also fine, but we just need to leave at least one. So that's why we delete one by one. So it's important to have this one by one addition. And now let us move to where we stopped. So we spoke about the properties of just weakly dominant strategies. That's the way we usually assume talk about strategies. And we spoke about that if we delete them, that leaves the maximum value of the player who's weakly dominant strategy we just deleted. It leaves intact, but it may change, only increase the maximum value of the other players. And therefore, the question is, very weakly, weakly. I'm only talking about weakly, unless I really emphasize this very weakly. Now, because we started with very weakly, I'm confusing with very weakly, but it should be weakly. So the question is, it's very abstract. So are weakly dominant strategies necessary? Are they indispensable? And let's see what we can say about it. So we can, first of all, find this nice example in this book, An Introduction to Game Theory by Osborne. It's only by Osborne, not the book by Osborne and Rubinstein. Okay, probably it's only by Osborne. Anyway, because they both have books. One is common to Osborne and Rubinstein. That's more famous than the one by Osborne. But anyway, in one of those books, I write here it's only by Osborne, that we can have a game. So look at the upper matrix, defines a game which has two Nash equilibria: top left, and bottom right. Now, bottom right consists of two weakly dominant strategies, but top left consists of no weakly dominant strategies. So it's an example that weakly dominant strategies can be indispensable, but we can say yeah, but we don't really like that equilibrium, which is composed from those weakly dominant strategies, because its profits are bad for both players. So let us talk about something else. Maybe we have another example, and we do, which that book does. So in this case, the equilibria are also top left and bottom right. Now, here, however, bottom right still consists of two weakly dominated strategies, but it's better for each player than top left, which consists of no weakly dominant. So actually, a weakly Nash equilibrium consisting of weakly dominated strategies only can be better than the other equilibrium. Moreover, not only can we have weakly dominated strategy in a Nash equilibrium, composing a Nash equilibrium, we can even have a game where there is only one equilibrium which is composed of weakly dominated strategy. Here the only equilibrium is bottom center, and it composed from the weakly dominated strategies bottom. It's weakly dominated by top, and from the weakly dominated strategies center, which is weakly dominated by left. So it seems that the weakly dominated strategies can be extremely important. It's true, but one of the important or one of the curious propositions which we don't prove and don't even use, but that's a nice thing which Osborne mentions, is that in a final game there exists a mixed Nash equilibrium with no weakly dominated strategy in the support. In particular, in the example beforehand, above, it means that there exists at least one other mixed Nash equilibrium besides bottom center. Bottom center is a mixed Nash equilibrium which is in particular pure, and it has only weakly dominated. Okay, so having seen that the weakly dominated strategies are quite important, let us now, regardless, sketch a general algorithm to find a mixed Nash equilibrium in a general game. No assumption about constant sum, potential, nothing. Now, given a game with n players, we did that mostly for 2 players, but let's talk about a general number of players. First, we iteratively delete all the strictly dominated strategies. In any order, we know that it will not change the set of mixed Nash equilibrium. Then, we find all the pure Nash equilibria by direct checking which pure strategies profiles can be, which are Nash equilibria. Then we find all the partially pure mixed Nash equilibrium. Now we do it in the following order. Partially pure means that some players play pure, some players mix. At least 2 strategies of players. Now, so when all the players play pure, we've tried this option that's called Nash equilibrium. So here we look at what if we are k, a minus 1 players play pure and the rest play mixed. And so on, k minus 1, k minus 2, till k and 1, till at least one player plays pure. The last case will be, of course, when nobody plays pure. But here we just look at that. And here we go, you see, in this order, because we use the fact that we already have checked those where you have other playing pure. And so we just use the fact that we assume that now we are checking when exactly k players play pure. And we go for any subset of size, all the subsets of size k, call it P. Now, for each assignment of pure strategies for P, it's quite a long loop, but again, mostly the small games, but I'm just sketching you, delineating the general strategy. For each assignment of pure strategies for these players, who we assume play pure, check whether the others n minus P can mix so as to allow the best responses of those n minus P to be mixed. Now, it means it's equivalent to say that there are multiple pure best responses, because if there are multiple pure best responses, a best response can also mix at least 2. Multiple means at least 2. If, on the other hand, there is at least exactly one pure best response, then of course no mixing is possible, but you always make it. I mean, any mix response will be strictly suboptimal. So we want to allow the best responses of each n minus p to be mixed, and allow the k taken pure strategies for those k players, so we have to assign them something, to also be best responses, what we have. So we can write that you have multiple pure best responses equations, and to allow the k taken pure strategies be best responses also inequalities. And finally, what about all the players mixing? Fully mixing, it's called fully mixed, yeah, all the players mixing. So we check now that what if all strategies are mixed, such that each player can best respond by a mixed strategy. And again, it means that it's equivalent to requiring that each player will have multiple, meaning at least 2 pure best responses. Now, please pay attention. When I'm saying fully mixed, I mean all the players mix. I'm talking about how many players mix. I don't mean necessarily that they have to mix between all their strategies. It would be a very interesting subcase, but I don't talk about it. I'm talking about that all players have to mix. And here I'm talking about K players who mix. I don't speak about how they mix. They can mix them on all their strategies, and it's the best response if and only if all their strategies, as pure strategies, give the same utility. They're all but that's exactly only then. So it's not like often. Of course, in our examples, you often will have only 2 strategies per player, so it will be simpler. Okay, having sketched this algorithm, let's just see a simple example. The battle of sexes. So you remember you have player 1, player 2. They want to go to different games, so they don't want to go separately, so they only get some non-zero utilities when they go to the same game. And player 1 prefers football, so when they are on football, player 1 gets 2, player 2 gets 1. While when they are on tennis, player 1 gets 1, player 2 gets 2. So in this game, the energy equilibria are of course football, and tennis. Now these are all of those pure. Now, since any pure strategy implies a pure best response, there is no partial mix. So if one is pure, the other has to be pure to best respond. And also, let's look at fully mixed equilibria. Now, in order to be fully mixed, now the column player, in order for it to have a motivation to mix, the row player has to play such probabilities p and 1 minus p that both best responses will be the same for column player. Otherwise, the column player will not have a motivation to mix. So the row player plays p and 1 minus p such that the choice of football for the column player, which gives 2p plus 0, or excuse me, 1p plus 0, because it's a column player, 1p, is equal to the choice of tennis for the column player, which gives 0 plus 2, 1 minus p, 2 times 1 minus p. That's the equation, and that means that p is 2/3. Similarly, the row player, see, each player mixes between already optimum strategies, otherwise it would not be a best response, but it mixes such that it will, in an equilibrium, it mixes such that the other player will also be motivated to mix. That's those equilibria we look for here. We are talking about fully mixed equilibria. So the row player implies that it should, in order for it to have a motivation to fully mix, regardless which strategy it chooses, it should have the same utility. So the row player should have the same utility for choosing football and for choosing tennis. And the Q, the probabilities of the column player, should satisfy that. So it means that when the row player chooses football, and thereby getting 2Q plus 0, 1 minus Q, so 2Q, it should be equal to here. What happens when the row player chooses tennis, and thereby getting 0Q plus 1 times 1 minus Q, 1 minus Q. So Q is equal to 1/3. And all the mixed equilibria are there for those. I'm just writing out the pure ones as probability of 1 playing football and 0 playing tennis. That's how I write them for football. Okay, because I need to write them. When I write them as a mixed equilibria, I want to write them in the same language of probability of mixing. Now let us talk about some subset of games, a very broad subset, but still a subset about which we can say more. We can tell more than we can tell about a general class of games, which are called constant sum games. Often people speak about zero sum games, but same properties we can at least see. What we do is to hold for constant sum game. It can be more general. So games we're talking about two-player games. It's a console time game. It's important that it's a two-player game because for more than two players, the properties don't hold, even if the time of the utility is always the same. So a two-player game is a constant time game. That's what we assume when we say constant time. Two-player game is a constant time game if there is a real constant such that the sum of the utilities is equal to the constant for any strategy process. For example, match in tennis, so that you have one, someone gets one, someone gets zero, but if the sum is always one. Chess, you know, winning utility by one, the losing utility by -1, and when they have a draw, then everyone gets zero. Then the sum is always zero. And rock, paper, scissors, and so on. Now definition. It's a reminder. And some X star is called the max minimizer. For player one, if for any X, any strategy of player one, it's the best player one can do when the second player tries to bring him down. So it's the best X relatively to any other X when the second player tries to minimize the utility of player one. And actually, it's reasonable for the second player to minimize because the utility is constant. Now, strategy of second player is a max minimizer for the second player if it's better than any other Y for second player, given that the first player tries to bring the second player down. And now we prove that. That's also a reminder that the relationship between max min and equilibria, that given a constant sum game with players, the utilities have a C. The following statements hold. The profile X star Y star is a Nash equilibrium. If it's a Nash equilibrium, then X star is a max minimizer of player 1, and Y star is a max minimizer of player 2. Statement 2, if X star Y star is Nash equilibrium, then looking at the utility of player 1 as a function of both player strategies, mixed strategies. Actually, no. It's just a game. It can be particular. It's already a mixed extension, but no, just any game. No mixing here. So the utility of player 1, when we max over the first player, then minimum over the second player, is the same as minimizing over the second player and then maximizing over the first player. First player, of course, wants to increase. That's the intuition between what I'm writing here. The second player wants to decrease, but the order here gives you the same result. And that's also equal to the utility of player 1 in the equilibrium. And this implies that all the Nash equilibria of this game have the same utilities. In particular, these are the player 1 gets all this max min, and player 2 gets C minus. C is the sum of their utilities. Now, in another direction, if we know that max min equals min max, and we have a max minimizer for player 1, call it X star, and we have a max minimizer for player 2, call it Y star, then it has to be an Nash equilibrium. So it's kind of both directions. Now, if we have a constant sum game, then its mixed extension is also a constant sum game with the same constant, which of course follows from the definition of this mixed linear basically utility. The above theorem implies, of course, then that. Remember that if given it, let me write the corollary proof. Given a finite constant sum game, where the sum of the utilities is C, for each max minimizer P star of player 1 and max minimizer Q star of player 2 in the mixed extension of this game, P star Q star will be a mixed Nash equilibrium. And max min will be equal to min max, will be equal to the utility in P star. Now that's exactly what we basically said. Simply that we know that max min is equal to mix max because we know that there exists a Nash equilibrium in a mixed extension of a finite game. So we know that the max min and the mix max will have this property which we wrote down. The only thing that we need to prove is that the maximum and the minimum are attained, which is something we assume that we need to prove. Now this does follow from the compactness of the delta SIs of those mixed strategies for finite games. Please don't confuse it with symphony games. For finite games. And from the continuity of the expectation, well, UI is defined as the expectation, so it continues in the probabilities, and its maximum and minimum also continues. So from that we know that eventually those are all obtained. Okay. Now that's the same statement, yeah. And we also can call this. Remember, since we said that when max min equal to mix max, we call this utility the value of the game. That's what we said in the lecture when we started studying constant sum games. Now, the mixed extension of the finite game always has a value. Since it always has max min equals min max, as I wrote here. Okay, that was just a simple follow up on what we did, and now I'll do something simple. Remember that we had this lemma that given the constant sum game, the constant sum is C. The max min of then you just maximize from the point of view of player 2 is equal to the constant minus min max. So please pay attention. Here we had max min and min max about the same expression. We just change the order. So max min player 1, player 2 of utility of player 1, and then player 2, player 1 of the utility of player 1. Here we have something else. We maximize the utility of player 2, max min, normal max min for player 2. Here we have C minus the utility of player 1, min max. So player 2 naturally wants to increase its utility, player 1 wants to stop it. Here we say that player 2 wants to decrease one's utility and player 1 wants to increase it. It's kind of the same because it's a constant sum, and indeed we showed in the lemma that it's the same. And also the argmax of this left expression is equal to the argument of the right expression. So we conclude that taking a max minimizer of player 1, regardless actually whether this is a mixed extension, no, not a mixed extension, whether there exists an equilibrium, no, it's always true. Taking a max minimizer of player 1 is equivalent to min maximizing player 2, and max minimizing player 2 is equivalent to min maximizing player 1. Take max minimizing of player 2 is min maximizing player 1, and so on for blah. Now, look at an example of election. So that's a story I invented. I think it's a nice story. Incumbent 1 decides whether to set high or low taxes, and the opposition leader chooses whether to publish some intimate photos of player 1. So they both want to be elected. So people don't like high taxes. I assume they just don't like high taxes. I don't think about maybe some of the taxes goes to themselves and not just to pay for someone else. In this case, I assume that it's a very socialistic state, so they just don't like paying for someone else. They don't like high taxes, but if they see the intimate pictures of the incumbent, then they go crazy. So then actually it's good to distract them with something else. Not the pictures, I mean. And then actually it's good that they may have this high tax, so that they get crazy about something else, forget about the picture. So in the in numbers, let's model the game as follows. So the incumbent is the role player, and she chooses whether to play high or low, and the opposition is the current player, and the opposition chooses whether to play to publish or to not publish, PONT. So it's a nice abbreviation, huh? So if the incumbent puts higher taxes, and then but nobody publishes photos, then as I said, we don't like high taxes, so the incumbent gets -2, and the opposition, of course, likes, because then the opposition person changes, chances have grown. Now, if, however, the opposition does publish the pictures, then actually it's better for the incumbent to put high taxes. Now, then incumbent will be better off if you put high taxes. Now, of course, you can say, why is it 1 and not something smaller? Yeah, it can be, but it's just an example. For the sake of looking at that, I think that, yeah, it could be made like -1, 1, because still there are two things people don't like: intimate pics and plus high taxes. No, but it does not matter here. I will not change it now. It's definitely not a point here. Now, low taxes also. If the pictures are published, then okay, low taxes don't distract and don't irritate people, but also they don't distract them. So when someone publishes the pictures, then your chances, I mean the incumbent person's chances, they plummet, but the chances of opposition grow. Now, but if the other person doesn't publish the games, then it's better, of course, to make low taxes, and then the incumbent chances grow and the opposition chances plummet. Actually, yeah. So the logic required that, of course, here will be something like -1, 1. Kind of ameliorates the damage of those pictures, maybe high taxes, but still it cannot be that if they are both negative. Some two negative events have happened that the incumbent event. Yeah. Anyway, in this matrix as this is a sub-zero game, and no Nash equilibrium exists. So first of all, we can just directly check that from HP. For example, the opposition wants to change non-publishing, because then it goes from -1 to 2, and then from HNP, the incumbent wants to low taxes, because then she changes from -1. Then from LNP, the opposition wants to go to publishing, because then she gets 1 instead of -1. And from L, it does not have to be a cycle. I'm just saying that for any point you have a profitable deviation. From LP, the incumbent wants to go to high taxes, because then she gets more than -1, namely she gets 1. Now, in addition to direct check, we can also conclude that there is no Nash equilibrium from the fact that max mean, the first player, which is maximum between the minimum that the second player can impose on her, and the second player can impose on the first player. What can she impose on him? Well, the first player chooses high. The worst you can get is if the second player plays P, it will be -1, and then so -1. Then when she chooses excuse me. Okay, I should look at other utilities. The utilities of the first player, when she plays high, are either 1 or -2. That's the first number. So the second player can impose -2. That. When the first player, the incumbent, plays low, the utilities can be -1 or 1, so it means that the first player can impose -1 as it was. The minimum here is -2 or -1, and the maximum between them is, of course, -1. Now, the min-max, on the other hand, is something else. What is the maximum that the first player can choose, given that the second player play P? The maximum the first player can choose by playing H is 1. What is the maximum that the first player can choose when the second player plays NP? It's by playing L, it's also 1. 1, 1, and then the second player has to minimize between those maxima, and that minimum between 1 and 1, so that's 1. And of course, -1 is strictly smaller than 1, so the max min and min max of U1 are not the same, so there is no Nash equilibrium else to be pure. Now, no pure Nash equilibrium, but what about the mixed extension? So first, let's look at what we can do using the constant sum property. You know that a mixed Nash equilibrium in general, pure mix, partially mixed, whatever, PQ is a mixed Nash equilibrium. If and only if it's a max min. So what are the max min? So look for the first player. Look what she gets when the second player chooses to play 1 second. Okay. When the second player plays publish, and the first player plays high taxes with probability P and low taxes with probability 1 minus P, then the utility that the first player obtains is 1 times P plus -1 times 1 minus P. That is and of course that's simply the line 2P minus 1. This line. It's going to be graphic, the solution. Then, when the second player plays non-published, then the utility of the first player, depending on P, will be -2P plus 1 times 1 minus P. So it's going to be 1 minus 3P, that line. Now, we want to find a max min. So what is the minimum given for a given P? What is the minimum the second player can impose on the first player? The minimum between those lines. It's here denoted by this fat pink line. And the maximum the first player can get from this minimum is the intersection point. And that's why exactly we're looking for this intersection between those lines. 1P minus 1 times 1 minus P, that's this line. It should be equal to this line. And then if P equals to 2/5, similarly to the other player. So if the first player incumbent plays high taxes, what are the utilities of the second player, given that she plays publishes probability Q and non-publishes probability 1 minus Q? It's minus q plus 2 times 1 minus q. So it's going to be 2 minus 3q. What are the utilities of the second player? When the first player plays float actors, it's 1q minus 1 minus q. So it's going to be 2q minus 1. And the minus, excuse me, the minimum, the worst that the first player can impose on the second player is a minimum between those lines. It's denoted here by the fat blue line. And the best between those points is, of course, this spike. And to find it exactly, we need to solve the equation. And that gives us q equals to 2/5. And there is only exactly one mixed equilibria. And now we can also employ a general method, which does not depend on the game being a constant sum. Here, we just go, I remind you, by the stage. So from no pure equilibrium, from what are the pure, partially mixed until fully mixed. Because this game is luckily not so large, so no pure equilibria exists. So that if one player plays purely, then the other has to react purely to be a best response. Best response. So this cannot be an equilibrium. So we only can have pure fully mixed equilibria. And each player has equal values for both strategies. Otherwise, there would be no reason to mix. So basically, having equal values for both strategies is equivalent to basically saying that a best response is mixed of a given player, that a given player mixes. And that gives us two equations. So for the incumbent, let's look at the equations. So in order to have the same utility from playing high and low, there has to hold that q minus q, excuse me, no, for high it's q minus 2 times 1 minus q. That has to be the same as, that's this equation, minus q plus 1 times 1 minus q. And for the other side, for the opponent, for the opposition, and plain published, the utility is minus p plus 1 times 1 minus p. And when playing non-published, the utility is 2p minus 1 times y minus p. And those have to be the same. And the equivalent and the equations are exactly as we saw before. So we've obtained the same results, luckily. Now another example of a zero-sum game where we use removing strictly dominant strategies. That's an example from Ron Holzman's lectures from the Technion, Israel Institute of Technology. He gave quite a nice course, so it had many nice examples and some nice proofs. And here the game is top, bottom, left, center, right. Here strategy R is strictly dominated by by the mixture of half the strategy L and half strategy center. Now, why is it strictly dominated? Because if we just look at half strategy L, we see here minus half, minus 2.5 0, half center will be 0 minus 2.5. And it's in total going to be minus 2.5, minus 2.5, which is both strictly better than minus 3 and minus 4. So this strategy of the column player 2, is strictly dominated. Therefore, we may delete it without changing the set of mixed Nash equilibria, obtaining this nice game. Here, Nash equilibria are symmetric. There are no Nash equilibria, we can just check it any place we start. It doesn't have to be a circle even. We don't look at it. We just can see that there is going to be, excuse me, there's going to be a profitable deviation at any position. So, for example, top center, moving from top to bottom is profitable from top left, moving from left to center is profitable for the other player, for the column player, and so on. So there are no Nash equilibria, no pure Nash equilibria. I mean, there are also no partially mixed equilibria, since a pure strategy of one player implies that the other player has to play purely in order to best respond. What I mean basically is that if, for example, player 1 plays C, the only best response for the second player is C. Player 1 plays B, the only best response for the second player is L. And the other way around. If player 2 plays L, the only best response for the first player is C. If player 2 plays C, the only best response for the first player is B. So there is no partially mixed equilibrium, and then let's go for the fully mixed equilibrium. Now pay attention, we are not solving it using that it's a zero sum. Oh, is it actually, wait a second. Aha, yeah, it's zero sum. Aha. Yeah, so we don't look for max min actually. Yes. Now, here we do look for max min. Because I start with the no way of, if you look for max min, you don't have to look at what are pure or what are partially mixed. You can just immediately look for max min. Okay. It seems that there may be a convolution of both methods. Okay, in the general method at least, after having found that there are no pure and no partial mixed equilibria, we look for full mixed equilibria. And that means that the reason to mix it means that both strategies have to display at the same value. So for player 1, top and bottom has to have the same value. It means that 5q plus 0, 5q has to be the same as 0q plus 5 times 1 minus q. And the solution is q equals to half. We don't solve it, but it's half. And for the other condition is that L and C, so left and center, has to be the same for player 2. And that also means that what player 2 gets from L, which is minus 5p plus 0, is equal to 0 minus 5 times 1 minus p. Now, yeah, it's I've not written those equations. I think I may have mixed. I think I may have mixed this slide. Where? Let me move the slide. So I've changed the slides now. So first we, as I said, finish the work, not using the fact that it's a zero sum or generally constant sum game. We just write those conditions that both players, each player is indifferent between those two strategies, and that's how we get P half and Q half. Now we use that it's a constant sum game, another approach, I mean, and we just find the max min. We don't distinguish between the various cases here. So we just need to tell, okay, what is the worst that each player can inflict upon the other player? So what is the worst that player 1 can inflict upon player 2, for example? If player 1, or excuse me, player 2 can inflict upon player 1. Now if player 2 plays L, player 1 can get 5p plus 0, 5p. If player 2 plays C, then player 1 can get 0p plus 5 1 minus p. So 5 minus 5p. The worst here is noted by the thick purple line, and the best from this worst that player 1 can get is the intersection between those two lines, and that described by equation 5p is equal to 5 minus 5p, so p equals to half, as expected what we already saw. Similarly, we find that q equals to half, so we have find the same result, and when we write the final answer, which remember that there is one strategy which we deleted, which is never used in an equilibrium, that was strictly dominated. That was the R strategy of the second player here. So we write the Mixed equilibria including zero probability to that strategy, zero weight, whatever you call it. Another example. Now, here pure energy equilibrium does exist, and that's AC. Now, one second. Now, what about mixed equilibria? So, of course, Nash equilibria, as we said, we identified when we play with the mixed equilibrium, when we deterministically play a given pure strategy. So AC is a subset of mixed equilibrium. Now, are there any more? Again, we have a constant sum game. The game is always zero, so we always have two options basically. Let's see, but again, we can play. We can always use whatever we want, of course, unless there is an exercise which tells us do that. We can always use whichever method we want. So, are any more mixed Nash equilibria? B is weakly dominated, but we cannot delete it because it's weakly dominated, right? When the other player plays C, B is equivalent to A. When the other player plays D, B is strictly worse than A because 0 is strictly limited. Now, if player 1 plays purely, then 2 has to best respond purely. So there is no mixed Nash equilibrium in that, or partially mixed Nash equilibrium in that. But if player 2 plays C, player 1 can mix because there are two best responding and D. And we require that what do we have here? The mixing has to be such that the utilities player one, the player one gets the same utility. Okay, player two plays C, player one plays. Player one has two inertia equilibria, so any mixing is the best response. Now we need to find probabilities P for A, action A, and Y minus P for action B, such that for the other player, because player A, when another player plays C, any action is the best response, any mixing is the best response. But for the other player, C has to be better than D. Now, how can we ensure that? What does player 2 get when playing C? Now, that player with probability P, so it gets minus 1 times P, minus P, minus 2 times P. Excuse me. Minus 1 times P, minus 1 times 1 minus P. Excuse me, that's what player, when player 2 plays C. So minus P minus 1 minus P. Now, it has to be better, at least as good, as player D, which gives her minus 2 times P plus 0. And this inequality gives us that P has to be at least half, because that's the only condition we have for all. And this includes the pure equilibrium of AC, right? Because in particular, P of 1, which deterministically plays A, is at least 1/2, so plane A, and we already assumed here to say that we played deterministically. So till now we have the thing that we have found till now, having looked at pure and partially mixed. It's plane C, deterministically, and plane A and B with probability P and Y minus P respectively, where P is at least half. Now finally, let's try to find mixed profiles. So P1 minus P and Q1 minus P. Pay attention, we don't use the null sum here. Maybe we'll use something in the future for this game, maybe not. But here we use this, it's a bit of an unusual example, right? Because we have this partially mixed equilibrium, that's good thing, a good thing to look at. Now, for fully mixed profile, we require that P's as such, both pure strategies are the same for the column player, for player 2. So that minus P minus 2 times, excuse me, minus P minus 1 minus P, that is equal to minus 2P, applying D, plus 0 times 1 minus P. So P is half. Now, for Q, what are the Q's? So that player 1 derives the same utility from A and B, or from A. It's Q plus 2, 1 minus Q. And for B, it's Q plus 0, 2 plus 0, 1 minus Q. So that's P half and Q1. And that's one of the half mixed profiles we have seen. Half mixed, not half mixed. So the half mixed set of profiles is basically everything. And the final answer is that the mixed Nash equilibria are exactly those P1 when P is half. Because I should write it in a different manner. It's not P1, it's P1 minus P. So it's clear that that one is 1 minus, but let me just write that 1 minus p and 1 0. So it's p 1 minus p for the row play and 1 0 for the column play. Let's wait till the slide will change. Okay, now let us dive into some more advanced, a little bit more advanced properties of the content that has changed.